we have solved the problem of a single degree freedom system, that is viscously damped when subjected to a harmonic excitation. In practice, of course, we know already that there are many other forms of energy dissipation, and not necessarily they will lead to linear equations which can be readily solved, like the viscously damped case. So, in such situation, what can be done, at least approximate solutions can be obtained if we can represent the damping by some equivalent viscous damping, and then we can use the results of a viscously damped system. So, now what we will do, we will find out the ways and means to determine an equivalent viscous damping for a case which is not viscously damped. Say, let us take a particular case, it can be anything, like a Coulomb damped system. Here the energy dissipation mechanism is different, it is not viscous, and the equations which we get, obviously it is not a linear equation that can be readily solved. We have solved the free vibration problem by using various techniques, but suppose if such a system is subjected to a harmonic excitation, what will be the response if we have to find out? So, one approximate way of managing this kind of a problem is that convert this system to an equivalent system where the stiffness, mass, etc. are same as the original one. Only thing what we have done, the Coulomb damping has been represented by a viscous damping here with a coefficient of damping C equivalent. Now, what will be the condition for this equivalence? One obvious thing comes to our mind is that the job of this damping mechanism is to dissipate energy. So, for the same amplitude, whatever may be the dissipation of energy per cycle, if that we maintain in the two cases as equal, we can give some logistic support to our consideration that this is an equivalent damping mechanism. Now, so to do that, let us first find out that in case of a viscously damped system, what is the energy dissipated per cycle. and say its amplitude of its displacement x is given as x when it is subjected to a harmonic force F0 cosine omega. What is the amount of energy dissipated per cycle? Now, here the only place where energy is being dissipated is this dash part, neither here nor here. So, therefore, let us see how much energy is being dissipated in this dash part. Now, at any instant, this position also has a displacement x, velocity x dot, etc. And the force which is acting here, we may call damping force F d, which is equal to C into x dot, where C is the coefficient of damping in this dash. So, at this instant, if it goes by an elemental distance dx, and this force, that means actually the force which is acting on this point is in this direction, and the force applied on this is this much. So, since this point is moving in this direction, it is subjected to a drag which can be represented as this. The energy lost due to this drag force because of this displacement dx will be dEd will be F d into dx. So, per cycle energy dissipated will be just integrated form of this for a whole cycle, and F d into dx, which we can write as F d is nothing but C into x dot, and dx can be written as dx dt into dt, and therefore, this can be written as C x dot square dt, t varying from 0 to a time period. Time period is nothing but 2 pi by the frequency, circular frequency, that is omega, that is the time period. Now, we know that x is capital X cosine omega t minus phi. So, x dot is nothing but minus omega x So, substituting it here, we get Ed is equal to C omega square x square sine square So, this is integrated over a full cycle. We know that this can be easily written as C omega x square sine theta d theta, theta is equal to this So, this is again for a full cycle from 0 to, we can make another transformation and we can easily make sine say psi d psi 0 to 2 pi square. And this is nothing but pi. I am not going through the detailed calculation, it is a standard result in trigonometry. the energy dissipated per cycle is pi c omega x. Now, here therefore, the energy dissipated per cycle will be pi C equivalent omega x square, and actual energy dissipated in the real system will be E d. So, therefore, we can always write that equivalent damping coefficient will be that which will be the energy dissipated per cycle in the real system divided by pi omega x. So, if you use this expression for the damping coefficient and use the results of the standard viscously damped single sticky freedom system under harmonic excitation, we can get the results. Maybe in this particular case we do it, but before we apply it to this, let us also find out that whether it matches the energy input. This is the amount of energy dissipated per cycle, but since the system is in steady state, that means its amplitude of oscillation does not change. So, the amount of energy dissipated per cycle must be replenished by the amount of energy input by the exciting force, which is doing work into the system. So, that can be easily found out that amount of energy input per cycle is nothing but F into dA. F is the applied, and this is again nothing but and finally we know x. So, therefore, x dot is already here. So, this will be now this minus sign we need not keep here. So, that is energy input, and if we solve this integration, we will get the result by standard result again, which will be you can do it pi x h 0 So, we get two different expressions, one for energy dissipation, other for energy input per cycle. The obvious question comes to the mind is, are these same? It must be same in the steady state. So, therefore, one has to substitute the expression for x and phi . So, using these two, it can be proved easily that E d and E I are same. And trigonometry, so I am avoiding it. So, you can show that E d is equal to when you substitute the expression for x from here, this will be the expression for ED. Similarly, when you substitute sin phi can be found out from tan phi. It will be square root of 1 plus cos square phi, inverse of that. So, therefore, using that one can also again show that this will be same thing. The algebra one can satisfy himself. So, therefore, ED is equal to EI in this steady state, which is a very obvious thing, because otherwise it will not be in steady state. So, therefore, the technique for solving a problem where the dissipation mechanism is not viscous and such a system is subjected to harmonic excitation and we have to find out the response, it is first better to find out the energy dissipated per cycle in the real actual system, then find out the equivalent damping coefficient for a system where the energy dissipation will be the same with this viscous damping, and then assume that system will have similar response, though the results will not be exact. It will give us only some approximate idea about the response of the system. So, if we apply, for example, to this particular case with Coulomb damping, what will be the response? Let us try to see. So, let us solve this problem and find out what will be the oscillation or the response. Now, first is to find out C equivalent. How did we find out C equivalent? That total energy dissipated per cycle in the real system divided by pi omega x square. How much is the, if suppose x is x cosine, that kind of a thing, if amplitude of oscillation is capital X, then for each half cycle the displacement of this Coulomb damper is 2x. So, energy loss will be simply 2Fx because friction force is constant. Similarly, on the other half cycle it will again have another displacement which is 2x, again the energy dissipated will be 2Fx. So, in total energy dissipated per cycle in case of this Coulomb damping is nothing but 4x into f. This is the total displacement and this is the constant force, friction force, which is opposing the relative motion, and so 4x into f is the energy dissipated. So, that will tell us equivalent damping is going to be so you find that equivalent damping coefficient, which will result in same energy dissipation per cycle, depends on x. It is not something like a system property, it depends on the result of the motion. Anyhow, once this is so, we know for a viscously damped system, x is nothing but F0 by k will use slightly different form of the result. This is the amplitude of oscillation. Phase difference we are not interested immediately. So, this is where we have applied this equivalent damping coefficient. Now, substituting this, C omega into sig equivalent into omega will be simply this So, what we get is actually an equation in capital X, but remember we should always use this approximation symbol. So, squaring both sides we get capital X square is approximately equal to and from this we get X will be approximately equal to so, this is the expected amplitude of oscillation of the Coulomb damped system when subjected to a harmonic excitation. But we have to always keep in mind that the result is very approximate, and all the characteristics which we find, for example, here it is found that f0 being less than 4f by pi, that it will have no amplitude because it is going to be imaginary. But in reality, if we apply a force to a Coulomb damped system whose magnitude is 4f by pi, which is more than f, because 4 is more than pi, so it is definitely going to oscillate with some positive and real amplitude. Similarly, we also notice that when the applied frequency is equal to the undamped natural frequency root over k by m, then denominator is 0, means that it will never approach any steady state. That means the characteristics will be similar to that of a undamped system with single degree freedom. So, this is a very important characteristics, but when we go, that means f0 is much larger than f, etc., then the value of x will be approximately equal to the value of x in the real case. But we should not try to make a deeper understanding using this expression for this system, because this does not satisfy the whole thing exactly. Anyhow, there may be other kinds of damping, like say structural damping. In structural damping, in most cases, energy dissipated per cycle is proportional to the square of the amplitude, or you can write that ED is equal to some coefficient, say I do not know, maybe lambda. So, in such cases equivalent damping will be where h is nothing but lambda by pi, and h is the coefficient of hysteretic damping. So, here of course, we find equivalent damping coefficient for a structural damping system is independent of x. So, for example, so therefore, if you have a beam, a cantilever, at the end there is a block and here. Now, if you want to solve this problem when this system is subjected to a dynamic force. This can be replaced by an equivalent system. This is K equivalent. The stiffness of the spring and this cantilever beam when a force is applied at the end is same, and the structural damping is replaced by so if the rigidity modulus of this be EI and length of this be L, then we know that when a unit load is applied here, the deflection of the system is L cube by EI. So, if the deflection is force divided by EI into L cube. So, its equivalent rigidity is going to be simply then EI by L cube. Similarly, C equivalent is going to be ED, which is C equivalent is going to be H by omega. So, when it is subjected to a harmonic force now, the displacement which we will get x will be F0 divided by where you have to just C equivalent omega is simply H. K equivalent is this. So, therefore, we get some, again remember it will be an approximate, because this equivalence is not exact. So, therefore, it gives us some method of approximately solving the cases where the dissipation is not viscous and the equations lead or the resulting equations of motion of the system will not be linear. We convert the system into an equivalent viscous damped system, find out the equivalent damping coefficient and treat the system as viscously damped. So far we have been discussing the cases where a dynamic system was being excited with the help of either a force or a moment applied at a suitable location. But it has been mentioned at the very beginning that there can be other method of excitation, and one very common and frequently found such situation is where the support of a system is oscillated. For example, if there is a pendulum, I can oscillate the pendulum by applying a force to the ball or the pendulum bob, but I can also oscillate it by oscillating the or moving the support of the pendulum. So, this kind of systems are called systems with base excitation. So, even this has lot of application also, because vehicles, that is where the whole vehicle is supported on springs and the wheels which touch the ground may be wavy. So, when it goes, the wheel is given an up and down motion. So, what will be the motion of the vehicle? Similarly, there can be many other situations where the excitation is not with the help of a force, but from a disturbance to its support. So, therefore, to represent the lump parameter model, and now we are exciting this mass not by applying a dynamic force here, but by providing a harmonic oscillation to the base or the foundation. It could be the other type also. So, this is very common, something is resting and ground is vibrating, or here this is vibrating, or a pendulum, the point of support or the hinge is oscillating. So, these are all cases of excitation given through a displacement of the support. Now, the equation of motion, we will try to solve this problem. Its displacement, velocity, acceleration, they are all this. The forces acting will depend on the amount of stress of the spring at any instant, which obviously will be then x minus y, because amount of stretch will be displacement here plus this minus displacement. Similarly, the damping force will be the relative velocity between the two ends of the dashpot. The equation of motion, therefore, mx2 dot is nothing but total force in this direction, which is minus c into x dot minus y dot minus k into x minus y, or we can rewrite this equation in this form. Now, y is already known as capital Y cosine omega t. So, therefore, this can be written as minus c omega y sin omega t plus k y. So, therefore, we find that right hand side again is a harmonic function of time. So, the equation becomes identical to what we have solved for force excitation. Only thing that f0 cosine omega t is being replaced by So, we can solve the equation, but as I have mentioned to you that sometimes it is much easier to solve a problem by using the technique of rotating vectors. So, let us apply that. So, this is the left hand side and this is the right hand side. So, these two must be equal. So, how much is kx? It is represented by a rotating vector small k capital X. Cx dot is represented by a vector leading this by 90 degrees and with a magnitude c omega x. Mx2 dot is this. And this must, that is, this result must be same as cy dot plus ky. Ky can be something like this, and cy dot will be another vector, rotating vector leading the y vector by 90 degrees, and this plus this must be equal to the sum of this from this differential equation, and the whole thing is rotating like a rigid body, as you know. And actually the real quantities are always projections of these onto one plane, in this case maybe the horizontal plane. So, one thing we find here, that the phase difference between the excitation, that is y, and the response, that is this, is this. But more importantly, let us find out the expression for x in terms of y and other quantities. So, we do one thing, we find out this length. How much is this? This can be this square plus this square, and this is equal to k minus m omega square x square, that is this square, and this is nothing but c omega x. And this must be ky square plus c omega y square or easily we get x square is equal to y square into now, if we divide both the numerator and denominator by a square, we get now c omega by k is nothing but 2 zeta r in terms of those parameters we should utilize now. And here it is again 1 minus r square whole square, again c omega by k whole square. Therefore, the magnification factor is by x by y is given by square root of so, this is the ratio of the response magnitude with the excitation magnitude. If you want to see the nature of this, how it varies, So, when zeta is 0, no damping, it will be 1 by 1 minus r square. So, it is our that is for zeta is equal to 0. Of course, we should always remember that we should do that. Now, when zeta is equal to infinity, extremely large, then this 1 is negligible, we can keep only 2 zeta whole square. Again this becomes negligible because zeta is very large. So, numerator and denominator is same irrespective of the value of r. So, m becomes independent of r and is equal to 1. So, that case is it is also easy to imagine that zeta infinity means it is a rigid connection. So, whatever will be x, same will be y, or whatever will be y, same will be x. Very in between, when zeta is increasing from 0, and so on. One thing we have noticed obviously that all these points, all these curves, they meet at one point here. That means the magnification factor for this kind of a system is equal to 1 when r is 0, because r is 0 means numerator is 1, denominator is 1. There is another value of r for which it is again always 0, that is r is equal to r square is equal to 2. So, it becomes 1 plus 2 zeta r whole square. Here it becomes again 1, because 1 minus 2 square is 1 plus 2 zeta. So, numerator and denominator is again same irrespective of the value of zeta. So, all the curves they pass through again a common point where r is equal to root 2. So, therefore, here also we find that in such a case the ratio of the response to the excitation depends on the damping coefficient or damping factor and the frequency ratio. So, for example, if we operate in this range, what happens? We get a substantial response if we provide some excitation. But if our natural frequency we design in such a way that the exciting frequency is much larger, then obviously you are operating somewhere here, r is very large, and then the response is much smaller than the excitation. So, though the ground may be vibrating substantially, the actual system on in which we are interested, its vibration will be small. We will come back to this point again, but before we close this particular discussion, let us solve a problem. So, we represent a vehicle In an extremely simple form, it is a block of mass m supported by just a spring stiffness k on the ground. Ground is a sine wave with periodic length, or with the length of one cycle is L, that is wavelength, and the variation, maximum variation from the mean position is capital Y. Now, we will give some numerical values. Here of course, this is x from its mean position, and the vehicle of course is moving in this direction with a velocity v. Now, from vehicle's point of view, we can consider the vehicle is stationary and the road is moving in the opposite direction. So, what will happen, that this point will be subjected to displacement y, which is nothing but y cosine omega t, if we consider t from here. Or simply we can say not omega t, v t. Now, we give the problem like this, that for a particular case m is given to be 450 kg, the speed is given as 96 kilometer per hour, wavelength of the sinusoidal road is approximately 6.1 meter. The variation, the amplitude of variation is 0.025 meter, that means 2.5 centimeter, 1 inch. The problem has three parts. First is, how much will be the k so that this system resonates. Number 2 will be, if x has to be 0.6 centimeter, what will be the value of k? And third part is, does the driver leaves his seat? If the seat and driver on which he is sitting gets disconnected. So, in this case obviously the equation of motion is simply mx2 dot is equal to minus a into x minus y, no damping, or mx2 dot plus kx is equal to k y cosine omega t, and where omega, we should keep in mind, omega is what? It is completing, when it is moving at a speed v, then how many cycles it will complete in unit time? It will be v by L. V is the distance moved in unit time, L is the distance required to complete one cycle. So, number of cycles completed in unit time will be v by L, and each complete cycle represents 2 pi of rotation of the vector, which represents this harmonic quantity. So, it is going to be 2 pi number of times. So, we can find out the k for which the natural frequency will be again same. So, therefore, we can say for part 1 to resonate the system to resonate, our 2 pi, now V will be equivalent to 96 kilometer per hour, which is equivalent to 27 meter per second. So, we have to find out this into 227 by 6.1 must be equal to square root of k by 450, and this will give us k has to be equal to 34 into 10 raised to 4 Newton per meter. Then the system will resonate. Next, we have to find out if it goes at this speed and the driver or this block mass has an amplitude of 0.6 centimeter, that means 0.006 meter, what will be the stiffness necessary? The second part, we know that x by y is given by square root of 1 plus 2 zeta r whole square but zeta is 0 in this case. So, therefore, this will be 1 by 1 minus sin, and this is equal to 0.006 divided by 0.025. This will lead to r is equal to 2.275. That means this is equal to omega by omega n. Omega we have already found out is this same speed, that means 2 pi v by L square root of k square root of n. So, 2 pi into 27 by 6.1 square root of 450, sorry, not square root of k and this m is 450, we can utilize here. So, this is a simple equation for k, and that will give us k is equal to 6.57 into 10 raised to 4 Newton per meter. So, that is the answer for the second part. Third part wants us to check that if during this motion whether the driver will leave the seat. Now, to do that we have to keep in mind that if this platform or the vehicle is moving up and down, and during the downward motion, if the acceleration with which the seat of the driver is falling down is more than g or just above g, then only driver, because he is falling under the action of gravity. So, if the seat's acceleration downward is more than that, more than the value of g, then he will leave the seat, he will float. So, you have to find out the acceleration of the maximum acceleration of the seat or the vehicle in the downward direction. So, maximum acceleration in the downward direction is equal to maximum will be omega square x. Now, under this condition omega is known, 2 pi into 27 by 6.1 square, and x is equal to 0.006. This we find is 4.6 meter per second, and this is less than 9.81, which is g. So, therefore, at any time the acceleration of the seat on which the driver is sitting is not going to fall or go down with an acceleration more than 4.6, and that being the maximum, which is far less than the acceleration due to gravity, the driver will be always on the seat. So, therefore, he is not going to leave the seat under this condition. This is a simple problem, but it illustrates the basic principle. We will take up further discussion on this.